science program before leaving to found a drug delivery company. But in 2012, he became bemused by how nuclear energy got so expensive, and tried to remedy that to prevent global climate change and make meaningful contribution to fighting the climate challenge. The result was an invention of the stable salt reactor and the creation of this company, Molten Energy. So with that, Ian.
Thanks very much to the organisers for inviting me here today. It's a pleasure to address this audience. My name's Ian Scott. I founded Molten Energy back in 2014 along with John Durham, who at that time was the founder of the Alvin Weinberg Foundation, set up with the vision of commercialising molten salt reactors, and that is exactly what we are setting out to do. The mission of Moltex is quite explicitly financial. We believe that nuclear energy will only make a real consequence to solving the global warming problem if it can be brought down to a cost where it is cheaper to use nuclear than it is to burn coal. This slide should be a very frightening slide to anybody listening to this. This is from the 2019 World Energy Outlook from the International Energy Agency. And it's worth looking at the curves here. There's some very good news on here. Solar, photovoltaic and wind power are both projected to grow to be very substantial parts of the world's energy production by 2040. That's where the good news ends, however. If you look at the curves of this graph for coal, all that's projected is that we will stop getting worse in our coal burning. That is just not good enough. It also shows that burning natural gas will continue to accelerate and virtually double over the period of time. So, in terms of climate change, this is very, very bad news. And this is realistic projections based on current technologies and current policies. The really depressing thing on this slide is a yellow curve at the bottom shows nuclear, which shows nuclear not increasing in any meaningful way in terms of total gigawatts of capacity. This is not what the world needs. So why is this happening? Why is the great promise of nuclear energy not being fulfilled? There's really two reasons, and this is a slide which is deliberately provocative. The twin drivers of the slow death of nuclear energy, because that is what we are facing now. The first driver is a massive increase in the capital cost. This is not news, but it is challenging the basic economics of reactors. There's a very good study came out from the EPRI in the USA looking at how nuclear's penetration in the USA would evolve at different capital price points. The message is very simple. If you can get your overnight capital cost down to $2,000 per kilowatt, then nuclear becomes a dominant power source. At $3,000 per kilowatt, nuclear becomes a significant contributor to power. Above that, and nuclear is essentially irrelevant and will not grow, will not roll out. Where are we compared to that $3,000 threshold for viability? Well, new pressurized water reactors are running at $7,000 to $8,000 per kilowatt and counting. That number is going up all the time. So that is only one part of the story. The second important factor, which is just as important as cost, is that the electricity markets are changing as renewables become cheaper and cheaper and penetrate deeper and deeper into markets. Renewables generate power at zero marginal cost, and that means that they will produce whatever the market says. As a result, there are times when baseload demand is entirely met by renewables, and there is simply no need for a power generation source which is always producing 24 hours a day, 7 days a week. You need a power source which can produce 24/7, but a power source that must produce 24/7 faces economic disaster. This slide is one that I have shamelessly borrowed, stolen from Charles Forsberg. He showed it some years ago. It shows the pictures on a particular day in Southern California of wholesale prices of electricity. And it shows in 2012 in red and 2017 in blue. What's happened between 2012 and 2017 was a major rollout of solar power. And the consequence has been that around the middle of the day, prices were going negative. Generators were literally paying the grid operator to take their power. That's not a great business proposition. That's getting worse. I'd like to show you some data from the UK now. This is for a full week period towards the end of May of this year. This is a period in May when the wind was blowing, the sun was shining. It was actually a very pleasant week. On the 22nd of May, the average day-ahead price for electricity was minus £9.92 a megawatt hour. So generators were paying that much for every megawatt hour that they produced. In fact, at one point in the early hours of that day, the price reached minus £52 per megawatt hour. The graph shows you the rate. There's substantial periods of time when prices are very, very substantially negative. So who's paying these negative prices? Well, two people, two organisations. One is nuclear. Nuclear cannot turn itself off quickly. The cost of coming back to power is too great. So nuclear will pay to have its power taken away. And the other contributor there are renewables who have strike prices. If they get guaranteed that we'll be paid £50 per megawatt hour, and they have to pay the grid £49 per megawatt hour to take the power away, they're still making £1. They will still produce, even though it's being produced at a clear loss. Such is the power of subsidies. So, put these two things together, and what is the real challenge that nuclear has to address? We need it to have a low enough capital and fixed operating costs, so it is profitable when it runs at between 30 and 50% capacity, and to be profitable in direct competition with unsubsidized fossil fuels. That's the target. And today nuclear is nowhere near achieving that target. So let me talk about capital cost. It will come as no surprise to this audience that the primary driver of costs in nuclear is actually safety. This is an interesting graph. I've used it for many years. It shows the overnight capital cost in constant 2014 money by date of completion of nuclear reactors. And up to about 1982, nuclear reactors were running at around $2,000 per kilowatt capital cost. Perfectly viable, well under that threshold, which is why they rolled out in very large numbers. After 1983, and the problems of Chernobyl in particular, and 3 Mile Island, costs skyrocketed. And today, you are running at costs 7,000 to 8,000, which is simply not a viable proposition. The key to eliminating hazards from nuclear reactors is actually molten salts. At two levels. This slide shows my very simplified description of a pressurized water reactor. You have a black pressure vessel on the outside, water inside at high temperature and pressure, and inside that you have tubes containing pellets of uranium oxide fuel. So let's start with the solid fuel pellets. These are remarkably finely engineered structures. They trap the fission gases inside the pores of the fuel. And you have something like 50 volumes of fission gas to every volume of pellet, and the pellets are about 95% solid with only 5% void. That means you're looking at internal pressures of many hundreds of bar. And the pellets hold those in extraordinarily effectively until they don't. And when they don't is when they reach about 1400 degrees centigrade, long short of any meltdown condition, at which point those pellets fall apart catastrophically, release large amounts of gas, rupture the tubes they're in, and release that highly radioactive gas into whatever containment you have around it. That's a fundamental hazard. We then take those intrinsically quite dangerous fuel pellets, we put them into a vessel surrounded by water at 300 degrees centigrade, which will, in the event of a pressure vessel failure, explode itself quite catastrophically. Boiler explosions are among the worst industrial accidents in history. Molten salts address this problem at two levels. In the fuel, they do not accumulate the fission product gases, and the most dangerous fission product gases, cesium and iodine, are not gases at all. They are stable salts, and they are only volatile when the salt actually boils. The secondary use of molten salts is as a coolant. Replacing water with a molten salt coolant means that you have a coolant which is chemically stable, operates atmospheric pressure, is not chemically reactive. At a stroke, you have eliminated two of the most important fundamental hazards of the reactor. So, there are essentially two ways that you can use molten salt fuel in a reactor. First way, shown on this slide, is what I call conventional MSRs, molten salt reactors. These are molten salt reactors based around the molten salt reactor experiment done back in the 1950s and 1960s. And the principle is that the fuel and the coolant are the same liquid. So the heat is generated in the liquid fuel. The liquid fuel is then pumped out of the reaction chamber where it was critical into heat exchangers where hopefully it's not critical anymore, and it passes the heat to do something useful with. Apparently relatively simple in principle. That means you are pumping an extraordinarily radioactive liquid at pressure around a relatively complex system with pumps, valves, heat exchangers, welded joints. And unless you've managed to produce the first plumbing system on the planet that can never spring a leak, you have to assume at some point there will be a leak. And then what do you do? It's a problem. It's not necessarily an insoluble problem, but engineering-wise, it's a very difficult problem. The second way, shown on the right-hand side of this slide, is the stable salt reactor technology platform. And this is the simple concept that you put the fuel salt into fuel tubes, rather similar to the fuel tubes used in conventional reactors. We're essentially replacing the uranium oxide with a molten salt. This is, believe it or not, a radically new concept. The patent was filed in 2014. It is now granted in most of the major jurisdictions worldwide. It is genuinely novel. It has sailed through the patent process with very, very little difficulty. It seems extraordinary that idea could actually be novel, but it is. And the reason it's novel is that it was actually considered back in the 1950s by the precursor of the molten salt reactor experiment, who considered putting molten salt fuel in fuel pins, because it's a pretty obvious thing to do. They concluded that it didn't work. And the reason they concluded it didn't work was that molten salts are actually quite poor conductors of heat. And they calculated that you couldn't get the heat out from molten salt. However, what is not in the published literature is that their conclusion was based on ignoring convection as a heat transfer process in molten salts. And heat transfer in liquids is dominated by convection. They made that assumption for a reason. They were designing an aircraft powering nuclear reactor, and that would have to be largely independent of the force and direction of gravity. And so they had to ignore gravity for convection. That decision was never revisited when people gave up on the idea of putting nuclear reactors into aeroplanes. until we reconsidered that 6 years ago. Okay, so this is a platform technology. Putting molten salt in tubes in a reactor is the basic platform technology. There are two implementations of that platform that Moltex is currently working on. First is a fast spectrum reactor that we call the SSRW, where W stands for waste burner. It's a reactor which is fueled by higher actinides recovered from conventional nuclear fuel. It's a chloride salt fuel. It uses a zirconium fluoride-based coolant salt. It operates continuously with on-power refueling, and it has completely passive emergency heat removal to the atmosphere. I'll talk a bit more about that reactor. The second one, which I'll say much less about, is a thermal spectrum version fueled by less than 5% low enriched uranium, conventional fuel supply, graphite moderated, but uniquely, I think, among molten salt reactors, the graphite does not contact the fuel. The fuel is a uranium sodium fluoride salt mixture. The coolant salt is proprietary. I'm sorry, I can't share what that is with you at this time. It has a very high output temperature, greater than 800 degrees centigrade, and again, it has entirely passive emergency heat removal. I won't say any more about the SSRU, the thermal spectrum reactor, at this stage. So we founded this company in 2014. Progress on developing the SSRW since then has been quite rapid. The master patent was filed in 2014 and granted in 2014, the same year the company was founded, which is unusual. By 2018, we had established Moltex Energy Canada and granted that company exclusive rights to the SSRW technology in North America. That same year, we signed an agreement with New Brunswick Power, leading to the development and deployment of this reactor at their Point Lepreau nuclear power plant's site. Since then, we've been working hard with the CNSC. We have almost completed the vendor design review. That will be completed this year, phase 1. We've received major investments from both established nuclear companies, and we are getting significant support from the Canadian government sources. We have also received very significant funding from the US ARPA-E research grants in the USA. So we have work going on at the US laboratories paid for very generously by the US government, which is a significant help, both financially, and there is some really excellent expertise there. But I will say a little about the actual design of the SSRW reactor. The fuel salt is a uranium plutonium chloride based fuel salt. Coolant salt, as I said before, is a zirconium fluoride, potassium fluoride based salt. That salt is in fuel tubes. The fuel tubes are vented. This is not a completely novel concept. This was done with a sodium fast reactor at Dunray in Scotland back in the 1970s. The reason that it is viable in this reactor is that the off gas is actually really very benign, because the cesium, iodine, and most of the fission products are non-volatile. The fuel assemblies are hexagonal. They resemble conventional fast reactor fuel assemblies quite closely. The core is approximately circular. The assemblies are supported on a diagrid. The fuel assemblies can be replaced while the reactor is at power by withdrawing the fuel assembly vertically, the vertical lift crane, which critically never touches the molten salt. Having a handling mechanism which has to go into the molten salt, as is done with sodium fast reactors with sodium, is a problem because it makes the mechanical failure of a lifting mechanism much more likely. A fuel assembly is taken out and then replaced. The ones that have been taken out are moved to the periphery of the reactor tank, where they decay for up to a year, and then removed as a batch through the airlock of the reactor into transport flasks for storage, disposal, or far preferably reprocessing through a mechanism which I will describe a little bit later. So now I'd like to talk about the fuel cycle. No use having a nuclear reactor if you don't have fuel for it. The SSRW is fueled with reactor-grade plutonium and higher actinides recovered from existing spent nuclear fuel. And as everybody knows, reprocessing is a commercially non-viable proposition. Nobody's ever made it make economic sense. And we're not into commercially non-viable propositions in Moltex. So the fuel cycle is important to us. So let me talk about reprocessing. Conventional reprocessing using variants of the Purex process is based on technologies designed to produce weapons-grade plutonium. That's for its purpose. And it does it very well. It produces plutonium of extremely high purity, well north of 99.5% purity. And in fact, if you're going to make MOX fuel for commercial reasons, you actually need that kind of purity. Those fuel pellets have to be very, very high specification, for all the reasons I said earlier on in this talk. For that, you need high purity plutonium. SSR fuel does not require high purity plutonium. In fact, it doesn't particularly want it. The plutonium for the SSR can be contaminated with more than its own volume of uranium, and it can contain quite a substantial amount of lanthanides, which is important because the lanthanides are the chemical which is actually quite hard to separate from plutonium. We don't separate it. So, the fact that we can tolerate this really very low purity plutonium opens us options for reprocessing which just don't exist without the SSRW reactor. And this, on one slide, is our process, we call it WATS, for converting waste into stable salt fuel. The input is CANDU spent fuel bundles. These contain about 20 kilograms of uranium. They have quite a low level of plutonium, about a little under 0.4%, which is lower than most because CANDU fuel is low burn-up. But for us, it's absolutely fine. We take these bundles clad in zircaloy. First step is we declad them using chlorine gas, a technology which was pioneered and demonstrated in the US laboratories. This produces zirconium tetrachloride as a one output, small amounts of gaseous waste from the pressurization gases, and pellets, uranium oxide pellets. Those pellets are fed into an electro-reducer. And the key novelty here is we don't simply reduce the pellets to uranium, we also add iron to the system. So they're actually reduced to a uranium-iron alloy. That's important because uranium-iron alloys melt at about 725 degrees centigrade, whereas uranium melts at 1100 plus. And so it is a far, far more practical proposition reducing at that temperature range. The output from the electroreducer is a uranium-iron alloy, which also contains the plutonium and higher actinides, a fraction of the lanthanides, all the noble metal fission products, and pretty much nothing else. The waste product from the electroreducer is a very concentrated electrolyte containing most of the radioactive fission products. The third step is to take that uranium alloy and to extract it by contacting it with a clean salt mixture containing an iron salt. The iron exchanges with the plutonium and the lanthanides, and a small amount of the uranium in the alloy extracts those actinides into the salt. A single contact will remove, or is predicted to remove, more than 98% of both the plutonium and americium into the salt. In our design, we have 2 successive contacts, so we recover essentially all of the higher actinides into the salt. Looked at in overall terms, what this process does, it converts about 99% by weight of the spent fuel into uranium iron alloy. This has essentially no decay heat, minimal radioactivity. It could be disposed of as intermediate level waste, or it can be stored at surface locations for future use. It contains uranium. At some point, uranium is going to become a valuable material. It will be a store of value for the future. The process produces about 0.4% of the weight of the spent fuel as our fuel stable salt reactor, and it produces about 0.7% by weight of a high level waste, which contains most of the reactor fission products but has a relatively short hazardous life because it is essentially completely actinide free. Storage or disposal of that is something which will be new to the nuclear industry, but is intrinsically less difficult thing to achieve than for the original spent fuel. I'd like to now talk about third key technology in the Moltex proposition. We call this grid reserve, and this is cheap gigawatt-hour scale energy storage. Going back to the slide I showed earlier, the real thing we need to achieve is economic operation at something like 30 to 50% capacity factor. And that is something which is challenging, but essential given the way electricity markets are evolving. Fortunately, the technology is actually already out there. Thermal energy storage has been pioneered in the concentrated solar power industry. The picture here is a concentrated solar power plant, mirrors in the desert, which is a wonderful system. It produces really good, high quality, high temperature heat around noon, when nobody really wants the power. And so this industry has pioneered storing thermal energy in large amounts so that you can store the midday energy and use it to produce electricity when people want it, which is often early evening. The technology used for that is actually a molten salt, pure coincidence, but it is a molten salt, it's molten nitrate salts, and it is a very cheap, very practical, and well-proven technology now. The picture on the bottom right of the screen actually shows the molten salt storage tanks associated with a solar power station. What we're using is essentially exactly the same. This slide shows how we intend to deploy the SSR reactor. We'd have a 500 megawatt output reactor, 500 megawatt electric, so about 1250 megawatt thermal. That heat output goes into the grid reserve thermal storage tanks. And those will feed boilers and turbines in our base case design at 3 times the power capacity of the reactor. So we have a 500 megawatt reactor driving a 1,500 megawatt power station. Economically, this is very important. The graph here shows the wholesale price of electricity in the UK. Now, the UK is a really very free market electricity system. It's highly competitive. It has a properly commercially determined price of power. And that price varies a lot over the day. So our model would be we would charge up grid reserve and not produce any electricity during the periods of the day when the electricity would have least value. And then we sell the power during the periods when the electricity will have the greatest value. Looking at the numbers, and again, this is for the UK, every country will be different. In the UK, over the 3-year period, 2017 to 2019, the system selling price averaged over the whole period was £47 per megawatt hour. If you just sold your electricity into the best 8 hours of each day, then that same electricity is worth £70 per megawatt hour. That's a premium of £23 per megawatt hour at a cost of adding in the grid reserve and the greater turbine capacity of about £7 per megawatt hour. It is an economic and business no-brainer to do this. It also has an interesting side effect on the economics of the system. Advanced nuclear technology, new technology, in fact all nuclear technology is high risk economically because nuclear energy has been known to have cost overruns every now and again. And investors are nervous because of that. The consequence of adding triple capacity turbines and grid reserve to the power plant is that the fraction of the total power plant cost, which is the nuclear bit, is relatively low. It's around about 40%. This means that if you have errors, and we do, everybody has errors in their assessment of nuclear costs, they don't make that much of a difference. So if that nuclear cost doubled, the impact on the overall capital cost is only about 25%. That brings the risk factor in building nuclear down really very substantially. So pulling this together, what does this mean? The economic benefits are, first of all, doing your safety right. Eliminate the hazards. Don't try to engineer solutions to those hazards. And secondly, use grid reserve so that you produce your power at the right time and you reduce the nuclear fraction of your power plant cost. This is the graph I showed before showing how power plant costs have escalated over the last 40 or so years. The stable salt reactor is at the end there. This is in the configuration where it has a 1,500 megawatt output and a 500 megawatt reactor. And you're looking at costs around $1,000 per kilowatt. That is extraordinary. It is extraordinary. Most important, you could triple the nuclear cost and still be very, very comfortably within the $2,000 to $3,000 region where you need to be for financial viability. This is enormously important commercially. It reduces the risk of the investment by a very large factor. So let me just summarize. The concept of putting molten salt fuel in essentially conventional fuel assemblies is a genuinely new concept. It eliminates a large number of the difficult engineering challenges that molten salt reactors face. The low nuclear island cost itself, coupled with the fact that the nuclear island is a relatively small part of the total cost, reduces the overall capital cost well below $2,000 per kilowatt, using conservative assumptions for optimism bias on our costs, with a really quite high confidence that that cost will not be exceeded. Thirdly, grid reserve, thermal energy storage, which I regret is available to everybody. I'd love it if we had that patented, we don't. Grid reserve makes nuclear energy a real partner to renewables in a market where renewables can produce electricity at essentially zero marginal cost. Energy storage is essential for commercial viability, and thermal energy storage is the way to achieve that. And finally, and far from least, the SSRW, the waste burner reactor, can detoxify the legacy waste from the first nuclear era. And that is something which is really quite important to developing the social license for nuclear in more countries. People worry a lot about nuclear waste. A solution to that which reduces its longevity and cost and potential impact on future generations goes a long way to make people accept nuclear energy. So I'll end there. Many thanks for your attention, and I hope you enjoyed the talk.
Thank you, Ian, for the great talk. So I think Ian has joined us online, and maybe you could unmute yourself, Ian, and thank you so much for this wonderful talk. And I think the ability to burn legacy nuclear waste and the ability to do thermal energy storage to have dispatchable power, as well as the safety characteristics, really makes this technology very unique. And you have worked through a tremendous amount of technical details with MOTEX. So we actually have one question. What is the pressure existing in the primary and secondary circuit? So I think I'd like to elaborate a little bit on that. So you do use molten salt coolant as well, right?
That's correct. So the pressure within the containment is zero, well, atmospheric. The pressure in the coolant as it goes through the pumps, you're looking at a pressure difference across the pump of approximately 3/4 of a bar. So throughout the system, the pressures are really very, very moderate.
Thank you. And I think in your talk you mentioned the molten salt fuel in the fuel rod is vented. So what kind of pressure is that? Because that is, I think, also related to the safety characteristics of the molten salt, because it was generally claimed that molten salt is non-dispersal. So, but have you considered, for example, if you have active radioactivity, maybe the volatility, the vapor pressure is not just thermally driven, but they're also, for example, radiation cascade driven volatility in the fuel salt?
So absolutely, the vapor pressure of the fuel salt during operation is completely dominated by the noble gas production in the reactor. The pressure is the same pressure as the containment. So these are vented. There's no possibility of accumulating any pressure buildup. The major potential release is actually through an indirect mechanism where the noble gases are evolved and leave the fuel tubes and then decay. And the big one, of course, is decay to cesium-137. The venting apparatus is designed, it actually has two successive chambers which the gases bubble out through. And we've calculated the extent to which the noble gas decay to cesium-137 will happen. And about 99.49% of the decay happens within the fuel tube. So the noble gas, the cesium derived, is almost entirely within the fuel tube. The exception to that is where you have production of cesium-135, which is a much less hazardous product than cesium-137, where about 5% of the xenon, which will decay to cesium-135, escapes the fuel assemblies and enters the containment. So we do have release of quite a small amount of radioactivity into the containment. Cesium-135 is relatively long half-life, low specific activity, but the containment has a conditioning system where the gas is continuously recirculated through filters. So that released gas, that small amount, is captured during the operation of the reactor. It does not release to atmosphere. And the amount that at any one time accumulates in the containment is such that if the containment was breached by some well beyond design basis accident, the amount of the cesium-135 that would be released is actually very small indeed. In fact, within the normal licensed release numbers for a reactor site.
Thank you. There is a question of the temperature and also related to corrosion. So how long do we expect the structural materials to last and the temperature?
That is a very, very good question. The corrosion in molten salts has been a major source of concern for all molten salt reactor vendors. In our case, it's actually particularly acute because we are looking at fuel tubes which have thin walls. And so you cannot rely on a slow corrosion rate to allow you to tolerate a low rate of corrosion. The way we manage this is by controlling the redox chemistry of both the coolant salt and the fuel salt. We do it by slightly different mechanisms, but in both cases, it is effectively a buffering of the redox potential to that of zirconium metal. Now, zirconium metal is a very strongly reducing metal. The only reason it doesn't burn in air is because it has a stable oxide film. Take the oxide film away, it will burn very happily, as indeed it has done in some accidents around the world. When you bring the redox potential of the salts down to that level, the thermodynamic tendency of chromium to be oxidized from the alloy into the salts, so converting chromium metal to chromium fluoride or chromium chloride is essentially eliminated. We are looking at equilibrium chromium fluoride or chloride concentrations down around 10 to the minus 10 parts of the salt, which is so low that corrosion is essentially impossible. Now, we will have to prove those thermodynamic calculations experimentally. We have the experiments in place to do that now, but it's a very, very high confidence that corrosion will be an effectively non-detectable phenomena.
Thank you. There's a question on waste. So if one uses high-level waste from reprocessed weapons, for example, to reduce in order to reduce the radiotoxicity from your waste plant, how will this affect the total volume of waste at the end?
Another very good point. So the great majority of the waste from our Watts plant is the uranium iron alloy from which the higher actinides have been extracted. The radioactivity of that alloy is basically controlled by the level of uranium-234 and uranium-236, which is produced during reactor operation, which is very low. So this would be definitely intermediate level waste. In some countries, it would be low-level waste. It's actually very country-specific, but is at the lower end of what's acceptable for intermediate-level waste. That's easily stored. The major radioactivity is in the electrolyte of the electroreduction cell, and there we reduce the volume of that waste by a factor of about 100 compared to the original spent fuel. So you move from having a highly radioactive, very large volume waste form to dispose of to having a very high radioactivity but very low volume waste to dispose of. Now, there's a number of ways you could think of doing that. You could do very extensive encapsulation of the waste in layers of metal and glass and plastic, and you could try to make sure it would never leak out and then bury it in a conventional geological repository. That's possible. Our preferred route is actually to dispose of this through a mechanism which has been pioneered in the USA, which is disposal in deep boreholes, where you drill down about 5 kilometers. You put the packages of waste at the bottom of the borehole and you fill it up. And that is, because of the depth, is an extraordinarily effective disposal method, but which is actually not compatible with burying very large volumes. These boreholes are only relatively narrow, and so the actual space for waste is limited. But our volume of waste is very small, and therefore borehole disposal becomes highly economical. We're actually looking at probably having a single borehole disposal route, just one borehole for each reprocessing plant that we build.
That's very interesting. I think this is like a general question for all the nuclear energy companies, which is what do you see as the main obstacles to physical demonstration, and also in terms of construction costs, because we know that a large part of nuclear power plant is actually not the nuclear island, but the conventional concrete groundwork and all these peripheral engineering aspects. So what do you see from 2020 that going ahead would be the biggest roadblock for ramping this up for doing demonstration?
So there's almost two questions in there. One is about what drives the excessively high cost. And you're right, as you get bigger and bigger, your concrete has to get thicker and thicker. So if you look at Hinkley Point C, they've just completed the biggest single pour of concrete ever achieved in the history of the world, which is a fantastic technical achievement, but having to do that is not good news. So the SSR is actually much smaller, much smaller. By volume, it's actually less than 5% the volume of an equivalent power PWR. And that reduces the whole concrete civil construction problem a lot. The second bit, however, is really very interesting, I think. In a pressurized water reactor, in fact, in most reactors, the secondary plant, the power conversion plant, is also a key part of the decay heat removal system. There's usually a fallback if that fails, but there is a safety function assigned to having the infrastructure in place to take the heat away.
Mm-hmm.
So long as that is the case, your secondary power plant has to be nuclear regulated. It may not have to, it's not a 10 to the 8 reliability, but it's probably a 10 to the 5, 10 to the 6 reliability. With the SSR, because of grid reserve, the reactor literally doesn't know or care whether the power plant is operating. All he cares about is there is space to put his heat into the storage tanks. So storage tanks can be nuclear regulated. They're very simple structures. The power plant is literally separated from the nuclear site. Now, what that means varies by country. So in Canada, the CNSC licenses activities, not sites. So you can have the power plant on the site, it's just not nuclear regulated because it has no nuclear safety function. In the UK, for example, the Office of Nuclear Regulation licenses sites, and anything on that site is nuclear regulated, in theory, including the canteen. It's quite light regulation for the canteen. So in the UK, you'd actually want to put the secondary plant outside of the site boundary, which is perfectly practical. It varies country to country. But the essential point is not to apply nuclear costs to that secondary plant. On its own, that's a very big cost saver.
What is the temperature of the thermal storage? I guess that's also a molten salt as well. Is that the same as the secondary? So what's the temperature involved?
So as long as you're using nitrate salts, and those are the cheapest and most commonly used and most well developed, your upper limit is around about 570 degrees centigrade.
Mm-hmm.
That's a good temperature because that's the temperature which will produce very good quality steam, which gives you high turbine efficiencies and low cost turbines. So it's a good place to be. Our reactor output is exactly that. We output at 570 degrees. So if you move to different storage mechanisms, so people are looking at storing in chloride salts, where your temperature has to go up to 800 to 900 degrees. That can be done, will be part of the future. We want to have, as far as possible, systems which are high technology readiness level. So the nitrate salts are well established. They've got operational experience. People know how to build them, and 570 degrees is fine for generating electricity. Not particularly good for thermochemical energy hydrogen production, for example, where you want higher temperatures. Those we are looking at achieving in the SSRU member of the technology platform. But that one we're not talking a lot about at the moment.
One last question. So if you roughly size it out in terms of, let's say, gigawatt electricity hour, then roughly how big are we thinking of in terms of the heat storage tank?
I don't have the number in my head. The cost of them actually comes to about between $2 and $3 per kilowatt hour of heat storage.
Of heat.
Sorry.
So if you convert to electricity,
of electricity capacity. I'm sorry. So
okay.
It's actually about $0.8 per kilowatt hour of heat.
That's like
that's very low.
Less than battery energy storage.
I mean, it's 2 orders of magnitude better than batteries currently. However, the biggest cost actually of the grid reserve system is not the storage. It's actually the extra turbines. So if you're going to store the energy and then use it over a shorter period of time, and there's no point having the storage unless you're going to do that, you actually have to have more turbine capacity. So we're looking at a 500 megawatt reactor with 1,500 megawatt turbine system. You know, those turbines cost money. And the major part of the additional cost of having grid reserve is actually the additional turbine capacity. The consequence of that is that you can actually put a lot of thermal energy storage. And one thing we're looking at the moment, quite seriously, is whether just being able to store for a significant fraction of the day is actually the best economic model, or whether it would actually be best to be able to store for 2 or 3 days and then output for 2 or 3 days. And the answer to that question is actually depends on the local power system. So if you're in a country with a lot of solar power, day-to-day variation is what you worry about, and a fraction of a day storage would be ideal. If you're in a country with a very large amount of wind power, wind tends to blow consistently for a few days before you come to a calm period. And so you'd want to be able to store for multiple days rather than multiple hours. And the low cost of the nitrate store and the fact that the major cost is the turbines actually allows you to do that. But we're still working on the detailed economics of that. It's quite complex.
Thank you, Ian, for this fascinating talk and for this very interactive QA period. Thank you very much.
It's been my pleasure. Thank you for inviting me.
Take care. Okay.